My name is Hugh Holbrook. I am on the software team at Arista. I've been at Arista for like a really long time, since the company was in Ken's living room. I work on lots of different things, but one of the things is the software that kind of is closer to the platforms. This is a little bit of a shift left from what we've just been talking about here, and a little bit more nitty-gritty, closer to the hardware and to the platforms. But it's all on top of a substrate of the same EOS operating system that runs everything, and comparable sort of network designs. So today I'm going to talk about networking for AI. Like, AI is all the buzz kind of everywhere. So I want to talk about networking for AI, and first just set up the backdrop of what you probably already know, which is kind of data center networking and how Arista does data center networking, and just a really quick recap. Then I want to talk about the structure of AI applications. And like, I'm not going to pretend to be an AI expert or machine learning wizard, but I know enough about AI applications. We have enough customers that I think I can extract some salient elements that highlight what's necessary to build performant networks for AI applications, which is important to a lot of our customers. And then I'll talk just a little bit about network designs for AI use cases. So this is a picture that you all have probably seen here, that is sort of the Arista Universal Cloud Network. This is a widely used design kind of across the industry. Leaf spine networks have been doing this for way more than 10 years. It's simple, it's stable, scalable. Performance is good, it's easy to automate. It's all based on open standards, IP. You can use any hardware switch, any routing protocols you want. It's automatable using tools like we have, and we have this proven in very large deployments. This is sort of a small 2-layer leaf spine network. We have lots of customers that scale it out by putting a tier 2 spine on top of these smaller spines to interconnect into bigger networks. And then you take this whole thing here, pods interconnected by a spine plane, and connect sort of, to get truly large data center or multi-data center scale networks, where I have hundreds of thousands or more servers connected, kind of with full bisection bandwidth. And this is what our hyperscalers are doing, and how their networks look. So this is like a very simple backdrop on data center networks. Is a picture of what they look like, which y'all know. And I want to, with that in mind, and of course EOS runs that, I want to talk about AI applications and how those relate, and what is different in AI applications compared to our kind of typical data center use case that we see. So I just want to talk briefly about artificial intelligence and what this means really for networking. As you all know, if you paying any attention to the media, AI long ago has made its way out of research labs, right? Deep learning has really made AI kind of a valuable tool to our customers and to lots of businesses, right? It's like doing machine translation, doing recommendation engines for things to show you on your news feed, recommendation engines for music you might want to listen to, videos you might want to watch, predictive advertising, medical image analysis, identifying tumors. Really has broad impacts, and it has a broad business value. And so the AI applications are increasingly important to our customers, to both our enterprise customers and our cloud customers, who are building out AI networks as a service to then allow their customers to run their AI applications on those. And so AI clusters are ultimately what's important, and it's clusters of AI servers, and I'll talk about why it's clusters instead of individual machines. And then networks to interconnect them is increasingly important. Not every AI application, but many of the most important AI applications that are driving things are built on top of a neural network. And you may know about neural networks. This is like a super simple, tiny little section of a neural network, but it fundamentally looks kind of like this. And there's lots of different types of neural networks, but you've got some data in, which might be an image, and it feeds into these circles, which are neurons of different types. And the neurons kind of take a weighted average of the inputs that they're getting, and then they use that to produce an output, and then they run that output through some sort of exponential function, like a sigmoid or a hyperbolic tangent or some function like that, to produce an output. and it can learn very complicated functions to the output from the input. And the output is typically, you know, an identification or a classification. It's like, okay, this one means it's a pink elephant, and this one means it's a gray kangaroo. This one, or it might be different dimensions of something you're learning. This is pink, and this is red, and this is green, and this output means it's an elephant, and this means it's a kangaroo, and this means it's a mouse. The neural network, like I said, each neuron is firing and it's producing an output strength, kind of some number. And the number that it's producing is sort of a weighted average of the input. And so each of these arcs along the neural network has weights. And the weights are trained, are learned by the neural network by providing different inputs. It's like might be hundreds of thousands of images are fed through it. And then the weights are adjusted based on how those perform to new values. And that's sort of the neural network process that like underlies many AI applications. So deep learning is a topic that you might have heard of. So a deep learning, that super simple like 2-layer network with inputs, outputs, and a hidden layer in between isn't sufficiently complicated to do the kinds of tasks of self-driving cars and image identification that there are in the industry. So deep learning just means bigger networks with more layers. So you've got multiple layers that might be a section of an image that are like then glued together into more neurons that are glued together, and each stage is learning more and more kind of abstract aspects of the data that you're presenting it, either the set of web pages or the snippet of language that you're trying to translate or the image that you're trying to classify. And the reason that people do, and this is a picture of a deep neural net without the individual neurons, because each of these boxes has thousands of neurons inside it. That's used for like image classification for like breast cancer. This is like from some research paper. But the reason that there are these deep neural networks is because the complicated models actually perform really well. Also, training them on more inputs, like more radiological images, more images, improves the accuracy. So the models internally can have like 50 million or 1 billion parameters, where the parameters are weights on the nodes and then weights on the edges between the nodes being the neurons. And then the weights themselves are trained on, it might be hundreds of thousands of inputs, if it's like, say, images, or if it's the Wikipedia corpus, you might be sending 400,000 documents through the neural net, and possibly many times. So this is computationally very expensive to iterate on this many parameters, feed the results back to identify errors and adjust the weights periodically. It's way too big for a single system to do. So you're forced to distribute this. These are gigantic matrix computations. You can see where this is going in terms of the importance of the network. This is from this is a quote from a paper from Facebook. Largely, most of the authors are from Facebook. And it's just like, without any exact numbers, it's kind of normalized, which is the size of their neural networks that they're building in terms of the parameters and in terms of the number of dimensions of how they're classifying things has grown kind of by an order of magnitude, like 10-fold, just over a period of 3 years. And like, why? Because there's a lot of value in what they're doing. It's like really valuable to them. Like they're able to translate it into value for their customers. They ultimately, make more money. And it's not just Facebook. This is data from Facebook, but many of our customers are seeing that and telling us that this is becoming a bigger and bigger thing. So this is kind of the structure of a common distributed AI application. And it's what I'll call it, what in the industry is called a data parallel. And there are other forms of parallelism. There's model parallel, but this is data parallel. And this is how I get really big models with really large training sets to work. Like when I can't run it on a single CPU or even a single GPU, because GPUs are very powerful. So in this data parallel model, the way it works is you distribute an initial neural net, like maybe it might be this complicated neural net, that deep neural net that I showed you for like image classification of like radiology data, to all the processors. And you might have like 256 GPUs all collaborating and working together on this. And there's weights on the edges and nodes. And then I take the training set, which might be thousands of images, and I split it up into batches, and I'm going to train different images on different processors. So I'll train like 10 processors on this one, and 10 on this one, and 10 on this one, and I've got 2,500 of them going, but I've got 256 processors, and they're each running in parallel. And then I'll run a batch of images through the neural net, like doing all that weight to produce the outputs. And then I'll compare what I think the output should be. If the inputs are labeled, I compare what the output should be. I'm like, oh, that's supposed to be a pink elephant, but it told me it was a red kangaroo. And so I go and increment the weights on the pink elephant output and flush that backward through the network. And then I decrement the weights of the red kangaroo and flush that backward through the network. And because I've done this all in parallel, if I was doing this just on one machine, I would iterate it like one time. But because I'm doing it in parallel, I want to take all of the learnings of all of my peer GPUs or peer systems and feed them into my numbers for future training. So there's a step where the parameters and the errors are shared across all of the GPUs participating. This is where it gets very computation intensive. Because remember, the number of parameters, which are fundamentally the weights on all these edges and the weights on the neurons, can be like 50 million or even a billion. People are talking about trillions of parameters in their models. So it's very, very large, and this is a lot of data. And what AI researchers find is that doing this, people have tried to do it asynchronously, but you actually get more accurate results and you converge faster if you do these updates synchronously across the network. So it creates a barrier effect where kind of everybody needs to share their parameters before I want to go on to the next training step. And so this puts kind of demands on the network to share that data quickly so that it can be the errors and the weights can be adjusted across all the models, and then I can go on to the next training step. So this is a data parallel model. There's also like there are model parallel ways to do it where like actually the neural network is sliced and like one GPU is working on one slice of neurons and a different GPU is working on a different slice, and that has different characteristics. But this is data parallel, which is pretty common and is I think a more typical way to structure large applications. So this parameter sharing that takes place for updating the weights, which is like a really important part of building the model. Not just it's not about executing the model, but it's about training the model. That tends to be the more computationally expensive, and this can take hours or days or weeks. So it's an important application to speed up. Is this kind of exchange and reduce phase where like I'm computing and running a bunch of images through my neural net, computing some errors, and then I exchange the errors and then like reduce all the errors I've seen from my peers. And that sort of compute, exchange, reduce cycle is kind of a fundamental driver of performance. And there's large messages being exchanged. And the messages are fundamentally sets of parameters that have changed. It's like, the ballpark is like, 1 megabyte to like 32 megabytes, can be bigger. But the large messages being exchanged is all inside a data center. So it's across short RTT. So this is like 10 microsecond kind of RTT within a data center. So it's not kind of your domain where like, long range TCP for like going to web servers works all that well. There's not a lot of entropy in the messages because I don't have a lot of flows. I'm just sharing the parameters, and it's typically done across a tree. So I don't have like hundreds of thousands of like, web pages I'm serving. It's like a small number of really big flows. And because of this barrier synchronization aspect, the stragglers, like one slow guy or one flow that's running slow, kind of prevents me from moving on to the next phase. And so the stragglers hurt performance. So these are kind of the characteristics that are kind of important to the applications. And now what does this demand of the networking? Is kind of the next step I want to move on to. Well, so what do I need? I need for starters, I want a high bandwidth network. I got big messages I want to send and it's time critical. I need something that's running at the latest and greatest speed. I need a transport protocol that can deliver that latest speed. That's not like built for like running over long RTTs and that ramps up slowly, that like operates well in this world where I gotta get to 400 gigabits quickly and start transmitting. I can't wait for a lot of round trip times to get there because I might only have 10 round trip times in my message. So, 10 megabytes at 400 gig, if I've done my math right, is I think about 200 microseconds. So it's not too many round trip times in your network. So the state of the art for this, and again, I'm trying to solve these problems over here, the problems of large messages, low entropy, and sort of this tail latency sensitivity. The state of the art is to use RDMA, which is, we'll talk about for fast transfer from memory to memory. ROCE v2, which is RDMA on top of that as a transport protocol. And I'll talk about each of these. DCQCN, which is a data center optimized congestion control protocol. PFC and ECN are network technologies in support of ROCE. And then a network design that can minimize flow collisions, or really a switching architecture that can minimize flow collisions to address this straggler problem where I have like one flow that's like the slow one that's holding everybody up. So I'm going to talk a little bit about RDMA here. So RDMA, really, this is something that I think is invention of, I don't know, the 90s, and it's sort of an evolution of computing. But the idea was to get the host operating system out of the way for transfers from memory to the network. And so it was really involving actually the NIC hardware to like suck data straight out of memory, drop it into packets, and send it across the network. And same way in the other way, data coming in from the network goes straight into the destination memory without getting stuck into a SKB in the Linux kernel and then getting copied into the user space or copied in multiple times. So it gives you kernel bypass, low latency, high bandwidth. It's really important if you're trying to get bandwidth and performance that's close to the limit, not just of what the network can deliver, but also what the memory system can deliver and what the PCI bus can deliver. All these things tend to be kind of move in lockstep because they all kind of go together. The PCI bus and the memory bandwidth, and the technologies are moving together. So remote RDMA is important. RDMA is sort of a way of getting the data in, and it's a set of APIs. But then in terms of a transport protocol on top of that and a sort of software stack, how do I do RDMA? There's something called ROCE, which is RDMA over converged Ethernet. This is actually something that came out of the InfiniBand Transport Association, out of IBTA. So there's InfiniBand payloads in here and InfiniBand transport protocols. But this is, I think, one of the good things, or the RDMA is one of the good things that came out of the InfiniBand world, is that a way to do RDMA. And so ROCE itself is this RDMA transport protocol running over IP and Ethernet. It's not running over InfiniBand, it's running over IP and Ethernet, UDP and IP and Ethernet. And ROCE v1 was Ethernet based, and ROCE v2 is based on IP and UDP. And that's a big improvement because nobody wants a giant like fabric running, just Ethernet. But like IP and UDP is good. So it gives us low latency transport. It's high bandwidth is what it's designed for because it's all in support of RDMA. It's using a different congestion control protocol, which is implemented kind of between the host and the NIC typically. And the one that's sort of the de facto standard today is DCQCN, Data Center QCN. It came out of a paper, and Microsoft really developed this back around 2015, I think. And it's congestion control optimized for getting to high bandwidth quickly in networks that have short round trip times. So it's like pretty different from the domain of typical TCP, which is trying to work well, long and short RTTs, and lots of different environments. ROCE depends on PFC and ECN in the network, and I'll just like do a little brief update on PFC and ECN and what those are. And it's also got some like host capability, host discovery capabilities in it. So PFC is one of the underpinnings of ROCE. So using ROCE requires a PFC implementation, and PFC is pretty simple. It's just like pause. It's like stop sending me stuff, but on a per priority or a per queue basis. So stop sending me your RDMA traffic of priority 2. Stop sending me your RDMA traffic of priority 3. But it's queue-based pause. ROCE builds on, works in conjunction with the DSCP to select to the transmit queue. There are 8 queues, and we use it to prevent drops because ROCE does not do well with drops. So it's just like the transport protocol is designed, kind of came out of this InfiniBand heritage where like the idea was that this was sort of a lossless transport, and drops, it doesn't handle them particularly gracefully. So PFC is a way to slow down the network and prevent traffic coming to me when I'm getting close to dropping it. And so there are drop thresholds, but basically, the gist of it is like I send a pause to my neighbor when my queues are getting full, and I send a start sending again message when my queues have drained. And the pause is sent to the link and on the cost value that I think is filling my queue. So it's sent on a specific link. It's not like all of my neighbors. It's like one output queue, because queues are typically output, but trying to identify which neighbor. So PFC is important, but it's really kind of a necessary evil. It's not actually good. PFC is the suspenders. The real belt is the congestion control algorithm in the transport protocol. So ideally, DCQCN would never cause drops in the network. You would have PFC would be unnecessary, and you would just be depending on the endpoints to adjust the because that does a much better job. PFC has a couple of pretty bad things. One is you can result in deadlock. That doesn't happen in most topologies. We can have PFC deadlock. You can be susceptible to NICs that have bad implementations and just like turn on pause, and that can like spread throughout your neck. And PFC causes, and pause of any kind causes head of line blocking, because it's a very blunt instrument. It's like my output queue is filling up, and I think it's you that's doing it. So I'm going to send you a pause, but I'm pausing all of your traffic, like not the one that's going just to the congested queue. It's stuff that's going to any queue. Yeah.
So I'm not a QoS engineer by any stretch, but these servers that they're connected to the network, what's the typical bandwidth interconnect? Is it 25 gig? Is it 100 gig? I mean, like. So
like the state of the art, like I think a pretty common AI, kind of a pretty high end, but sort of common AI attachment is like an NVIDIA DGX A100 box, or a DGX 100 box with NVIDIA A100 chips, and they have like 200 gig NICs in them. So they can support eight 200 gig NICs. So it's pretty high end, right? So like the GPUs are special purpose designed things to like crank through tons of bandwidth, because this is really like CPU intensive, because they have like networks to match. So they're probably the highest bandwidth end stations that we see. And you think that those GPUs are going to overdrive the bandwidth capabilities of those NICs at that rate? Otherwise, we wouldn't need QoS. It's like, you know, the answer to QoS was big. There's two places where you can actually see congestion inside the hosts. Like the PCI bus can be congested, the memory bus can be congested, et cetera. And we can actually see it in the switches because of fan-in. So you can have fan-in that happens just like two flows simultaneously going to the same output port. I can get collisions inside the network at, you know, between the leaf and the spine, because there's not a lot of flows, so sometimes they collide. And that can cause congestion. And then you quickly fill up your buffers if I'm blasting at close to wire speed, because I'm trying to hit it.
So doesn't this make an argument for system design models that integrate both the GPU powered NIC and the top of rack switch to get that end-to-end flow? Because as we think about like the bigger pictures, I'm thinking about converged and composable infrastructure, the ability to address memory from one CPU and one system to another system. Isn't that type of visibility needed to do stuff like flow control?
This is a very active area. There's a lot of interest in improving this. There are other things in the mix that people are looking at. There's other like DCQCN is probably not going to be the best congestion control algorithm for all time. There's something called HPCC, which like, you know, tags packets as they flow through the network with, you know, where they went. So there are more things in this space, and like this is just kind of the state of the art today. It's not actually that, like, it's not that amazing, but so yeah. So there are some features that you really want that, like, you know, that we support in our feature that we've learned that you need in your network. Things like, you know, per port, per queue, PFC configuration of thresholds, PFC watchdog, buffer tuning, asymmetric pause. And one big thing is that deep buffers really help, because you only send a pause when I'm getting close to my queue being full. And if my queue is deeper, I send pause that much less often. And that can make a really important difference on these workloads that are really critical. ECN is another technology which just marks packets when the queues are getting full. I won't go into too much depth about ECN, but it basically signals the transport protocol to slow down. You need an ECN algorithm that works in conjunction with some kind of active queue management like WRED. So what does this mean in terms of, you know, the interconnects that we see people using for these AI and ML applications? Well, one that works like just like super well is if you can just take a 7800 chassis and connect your GPUs directly to the 7800 chassis. The scale is actually quite impressive. So we got 576 400 gig ports we're shipping today in a 16 slot chassis. It can be 1152, 200 gig ports. It's got deep buffers. The fabric itself is a lossless fabric. So even though it's multiple chips inside it, and like inside, you may have heard us talk about it before, it's like a Clo fabric inside, but it's congestion free. The reason it's congestion free, and I won't go into this slide in any detail, but like the internal fabric, which is a Clo fabric, is a cell fabric. And so packets are sprayed across all the paths inside the box. So there's no hot spots. I never get any like hot flow paths where I get two flows colliding on the same path as I would if I built sort of a 2-layer leaf spine with the same bandwidth. There's lots of buffering because of the use of HBM and large buffers in the VOQ fabric. For even larger fabrics, and we see customers that are succeeding like this today, we have two-layer fabric with a 7800 spine and kind of TORs that can be deep buffered or not. You can build up to large fabrics with thousands and thousands of GPUs in them, going beyond the scale of what you can interconnect with a single 7800.
So that, just to touch on the, you don't have that fan-in problem on the Clo network inside the chassis. Is that you're just basically doing per packet load balancing at that point?
It's actually packets are sliced into cells. Yeah, and then the cells are per cell load balance, so it's even more than that. And then there's actually a reordering on the egress that like, so you can kind of spray randomly or actually round robin across the fabric and get super good load balancing without any kind of like, there's no elephant flows because it's not flow-based load balancing. It's like random packet load balancing. It works really, really well. And so you can kind of drive it. It's basically within the chassis, it's completely lossless. So you just never see congestion. It's congestion-free and loss-free.
Is it a 53-byte cell?
No, no, like that far. Like
I'm old.
Yeah, no, it's like it's better than ATM. I think we've learned something from there. But there's this like 256 byte, and the cells can be larger for efficiency. So I guess just to summarize, we've got. I think one of the important things is to build a fast network, and building merchant silicon that rides Moore's law to kind of get from 100 gig to 200 gig to 400 gigs is super important. Like that's the biggest thing you can do is be at 400 gig when 400 gig is ready for your AI network. It's like all the other optimizations are small compared to being on the next process node because it's like a 2x improvement. Getting to scale is important. The architecture to support RDMA is something that we've built up for years with our customers. And then the deep buffers and the congestion-free architecture have been a really valuable aspect of the 7800.